You know that thick, sticky, heavy feeling on a hot summer day? Yup, that's humidity. But what is it really, and how does it work? Well, we're going to get into the surprising science behind the water you can't see, but can definitely feel.
So get this. Even on the most sweltering, tropical, soak through your shirt kind of day, water vapor makes up at its absolute maximum only about 4% of the air we're breathing. Yeah, that's it. Just 4%.
So that's the big mystery, isn't it? How can something that's such a tiny piece of the puzzle be the single most important gas when it comes to what's happening in our atmosphere? Well, it's because despite that small number, water vapor is basically the MVP of atmospheric processes. It's the secret ingredient, the hidden power that drives everything from a gentle morning fog to a massive thunderstorm.
But, to really get a handle on that power, we first have to figure out how scientists actually measure it. Because it turns out the way you measure humidity completely changes the game.
So how do you measure something you literally can't see? Well, meteorologists have a few tricks up their sleeve, but not all of them are created equal, especially when you're talking about air that's constantly on the move. Okay, so the most intuitive way to do it is something called absolute humidity. It's super straightforward. You just measure the mass of the water vapor inside a specific box of air, say a cubic meter. It's basically just a density measurement. Simple enough, right? Well, here's the catch. Air doesn't just sit still. As a chunk of air moves up and down in the atmosphere, changes in temperature and pressure make it expand and contract, so its volume is always changing. And that means its absolute humidity is also changing, even if not a single drop of water was added or taken away. For a meteorologist, that makes the number pretty much useless for tracking weather systems. What a headache. So to get around this, they came up with something much, much smarter: the mixing ratio. Instead of comparing water vapor to an unstable volume, it compares the mass of the water vapor to the mass of the dry air it's in. And you can see right here why this is the go-to method. Volume is shaky, it changes all the time. But mass is constant. It doesn't change when temperature or pressure does. So this gives meteorologists a solid, reliable number they can actually work with as an air mass travels. All right, so we know how to measure it. Now let's dig into the real physics of it. I want you to imagine a sealed container. At the bottom, you've got some water, and above it, you've got totally dry air. This little thought experiment is going to be key to understanding when the air is officially full. So here's what happens. Right away, water molecules start jumping out of the liquid and into the air. That's evaporation. As these molecules zip around, they start to create a tiny bit of pressure, but it's a two-way street. The more molecules there are in the air, the more likely some of them are to bump back into the water and stick. That's condensation. Eventually, you hit this perfect sweet spot, a point of equilibrium, where the number of molecules leaving the water is exactly equal to the number of molecules returning. And that point of balance is what we call saturation. It means at that specific temperature, the air is holding the absolute maximum amount of water vapor it can possibly handle. It's full. But what decides what that maximum amount is? This brings us to the single most important piece of the puzzle, the king of this whole process: temperature. So let's go back to our container. It's hit that perfect saturation point. Now, what do you think happens if we start to crank up the heat? Okay, check this out. The numbers here are just wild. At a cool 10 degrees Celsius, a kilogram of air is totally saturated with just 7 grams of water vapor. But warm it up to 20 degrees and boom, it can hold 14 grams. Double. Heat it up again to 30 degrees and it can hold a whopping 26.5 grams. The capacity of the air to hold water vapor literally almost doubles with every 10-degree jump in temperature. So this is the big aha moment. The amount of water vapor needed to saturate the air depends entirely on its temperature. Warmer air isn't just warmer, it has a hugely, exponentially greater capacity to hold moisture, and that is why a humid 86-degree day feels 1,000 times more oppressive than a humid 50-degree day. All right, let's take all this science out of the lab and see how it plays out in the real world. This core principle actually explains some pretty strange things you've probably seen outside. You ever notice this? A few days go by after a big snowstorm, and the snowbanks are definitely smaller, even though the thermometer never once climbed above freezing. So where did the snow go? I mean, it didn't melt, right? Well, the answer is this really cool process called sublimation. It's what happens when a solid, like an ice crystal, turns directly into a gas, water vapor, completely skipping the liquid phase.
So picture this. It's a cold but really sunny day. The air is super dry, which means it's nowhere near saturated. It's thirsty. The energy from the sun gives the little ice crystals in the snowbank just enough of a kick to escape directly into that thirsty air as water vapor. And so, molecule by molecule, the snow pile just vanishes into the atmosphere. So, from the dew on the grass to the formation of massive clouds, this relationship between temperature and water vapor is the hidden engine driving so much of our weather. Now that you've got the secret key that temperature controls the air's capacity for moisture, what other weather events out there do you think are secretly being driven by humidity? It's something to think about next time you step outside and really feel the air around you.